Okay, good afternoon. I think it's time to start. So the chair of the afternoon is Professoressa Gabriella Sartorelli.
I am. Good afternoon to everybody. I'm very pleased to be here, indeed. I have seen this. It's a very interesting school, indeed. And I'm sure that everybody is very interested in following everything. And this afternoon, there will be this, the argument is a very important one. It's the screening of materials that is, as maybe you already understood, a very important ingredient for the success of any underground physics experiment. But let's go directly now to present our speaker. He is very well, he knows very well the matter, of course. He is Roberto Santorelli, and Sartorelli, okay? And you know, I remember very well him because years ago, many years ago, when he was still a younger physicist, maybe PhD student, I don't remember well, in Gran Sasso, sometime his boss was asking, his supervisor, let's say that, was calling me instead of Santorelli because of it was very near in the agenda, you know. Okay, now is time was gone since that time, and indeed is now 20 years is involved in the noble liquids experiments and technique, let's say better. Previous with xenon and now with argon. And so he started time ago with the dark side experiment. Indeed, he is now a member of the dark side experiment and is responsible, of course, of the material characterization. And is now not yet a young PhD student, but is a staff researcher at CMAT at Madrid. And on top of everything, I guess, is a very mad fan of the Napoli football club. So, okay, so now we leave the place to Roberto, and we will listen to any interesting things he's going to tell us. Please, Roberto, welcome.
Thank you for this nice introduction. I'm very happy to be here at this very interesting school. Can you see my screen?
Yes.
Can you see also the cursor?
Now it's full screen.
The pointer is there, right?
Yes, okay. The arrow. Okay.
Very good. So let's start setting a bit the general concept of this lecture. After this class, in principle, we should be able to know the most important sources of natural radioactivity, understand the principle of equilibrium and disequilibrium in the decay chain, get the principle of the cosmogenic production of radionuclides, understand the problem given by Radon 222 for low background experiment, and understand the importance of the material assay and the radio purity in this kind of, in this field, and know the principle of the most used technique for the assays of the material. What you are supposed to know to follow this lecture, indeed very little, just basic principle of nuclear particle physics. So principle of radioactive decay, nuclear radiation, interaction of particle with matter, in general aspect related to rare event research and low background techniques. I'm sure you are a bit familiar with this technique since this school is mostly for underground physics. Now, literature, there are just two reviews, quite old, but still a good starting point, quite complete. Then two papers a little bit more specific on two aspects, two textbooks. And although my suggestion is always to, if you want to get a little bit more in this business of the radio purity of the materials, maybe you should read the papers, the material assay papers for several low background experiments like xenon, exon, LZ, and so on. Now, starting point. Okay, this is basically what we want to do. This is the physics that we want to do: dark matter, neutrinos double beta decay, geoneutrinos, supernova neutrinos. So it's not very nice physics, very interesting. There are two problems. The first one is that our region of interest between, let's say, don't take these as sharp limits, but let's say we are in the keV, MeV, 10 MeV range. It's already occupied by the nuclear physics. Then we want to detect few events, rates as low as few events per year, or maybe one event per year, or even less. Okay, in order to do that, we developed along the past decades very nice technologies. We optimized the detector design. It's very challenging, obviously, to detect few events in the background given by the natural radiation, natural radioactivity. So we developed very fancy technique which are able to filter these few interesting events under of many orders of magnitude more abundant background. This is, for example, based on data mining, machine learning. Okay, that's very nice, but there are two basic concepts. That's our starting point. The two concepts for this kind of physics that we want to increase the mass of our detector, and we want at the same time to reduce the background. These are two pillars of this investigation. You can see here, for example, that's just an example of the evolution of the Xenon project. It moved from Xenon 10 to 100, 1 ton, and ton. Okay, and then on the right, I put just to give the concept how important is background. This is a single phase detector, liquid argon. I had once in the lab. You can see that how different is the spectra taken in two different background conditions. So the same detector with the same active volume, but two different background conditions. In the low background environment, you see structure that are hidden or shadowed in high background. So these are two pillars. We want to increase the mass and reduce the background. What kind of background? Obviously, you know, we have cosmic ray, environmental radioactivity, airborne activity from radon, but there is a specific and very peculiar background given by the intrinsic contamination of the detector. This has to be, first of all, precisely understood, because you cannot build a detector just using random materials. This contamination has to be precisely measured before the detector is constructed. And at the same time, it's a very difficult task. Why? Because even minimal level of alpha, betas, and gammas surrounding the active volume, so the material of the detector, can pose an important background for the signal that you want to detect. As I said, it's difficult to reduce this background. There is limited impact of active or passive shield. Obviously, it's nearly ineffective to go underground because the detector is to be constructed by materials, and the materials itself emit this kind of radiation in whatever condition, above or below ground. Now, a simple strategy to minimize this background to some extent is minimize the amount of material that we use. I think this discussion could be compared a bit to the work of dietologists, is called, or nutritionists, or something like that. You know, if you want to get slim, and then you in this case you want to get less background. Before talking about calories, it would be better to eat less, so to use less materials. But that is effective to some extent. Ultimately, we have to build our detector. Then there are other problems given by the fact that you cannot minimize the material because of mechanical problems, because of safety problems that you have. So at the end, we always have to come to the radio purity, which is crucial for the sensitivity that we want to achieve for rare event searches. Now, the radio contamination of the material cannot be zero, okay? Because the raw material that we use to build the detector are usually contaminated when at the origin, when they are on the ground, and the material itself may be made of elements that have radioisotopes. Now, this is a bit a frontier aspect for our investigation, because as I said, it's very difficult to reduce this kind of background. That is what we want to do. So over time, there has been a great interest in developing experimental techniques which are necessary to verify, measure, verify, and maintain the radio purity of the detectors for rare event research. It is a frontier aspect of our investigation. This, for example, can be demonstrated by this plot. This is from DarkSide, an experiment that probably you know at LNGS, DarkSide 50. You see, that's the background model, background spectra that you see. All the components have been identified, and you can see from the label that are from the cryostat, the sensor of the detector, the structure, or even from the argon itself. Okay, so that's the ultimate material, the ultimate background for this kind of experiment. Strategy. We are setting the stage. Okay, let me define a bit more in detail the strategy that we have. We need dedicated measurement to ensure the radio purity of the materials using the detector construction. We have to quantify the level of radio purity. Let me anticipate, we will go through the techniques in the second part of the talk. Let me anticipate that we don't have just one technique. Unfortunately, it's necessary, depending on the specific contaminant that we want to assess, that we want to measure. We have different counting methods that have to be employed for this kind of research. That's not even the end of the story, because we cannot just measure sample of the material. It could be not enough. The level of radio purity of measured sample can be different from different provider. And then the contamination can be different even from the same provider in different batch. So the story, I mean, there is no free lunch in this business, okay? The story is quite complicated. And there are different steps that have to be fulfilled in the entire chain before filling the data, before constructing the detector, from the assay to the purchase of the material. Keep in mind that once you have secured a batch that you think that is the good one for your detector, this doesn't mean necessarily that is the contamination that you will get in your detector, because once the raw material has been purchased, the radio purity of the final part, the final component of the detector can be different, because the material, the component, the part can be contaminated during the manufacturing process. So by, I mean, intentional or unintentional, due to the addition of radio-contaminated catalyst or using just dirty molds, and so on. And then at the very end of the story, once you have the part in your hands, so the part that you have to use to build the detector, that has to be stored properly in a clean environment, typically underground and protected against radon. Now, just last slide to set the stage. Is this an art? I found this sentence in this paper. I like this, so I put it over there. So selecting candidate low radioactivity materials is much an art as a science. That's probably because, you know, as Italian, I'm a bit obsessed with art. And, you know, sometimes we say that if what you do is not art, it doesn't deserve to be done. So I put this sentence over there. I'm not sure in reality this is an art, but it certainly heavily rely on the experience of the experimentalists and on the previous data. That's something that that you have to take into account, you know, the previous measurement, your experience, in order to minimize the material assay campaign, because this task takes a significant amount of time, cost, and enormous effort to assay each single part of your detector. All the materials have to be selected carefully, and obviously, I would say more than access at the end of the previous measurement, maybe it would be good in this community to propagate the information that you have for the future experiment. Now, let's come to the first part of the talk, that is what we have to measure. I think that you are familiar with this chart, is the radioactivity chart, the radionuclide chart. Once it was called the Segre chart. You know, we have, these are all the kind of possible nuclides. They are plotted following the Z number, so the number of protons and the number of neutrons. We have this stability region, stability valley in the middle, where more or less the number of protons is equal to the number of neutrons, at least for the first part. Then, according to the Shell model of the nucleus, we need an excess of neutrons to make the nucleus stable. And then we have all the other radioactive nuclei, which tend to, the decay tend to push the nucleus toward the stability valley. Basically, the heaviest stable element is lead, and then we have a natural element up to uranium. I assume that you are also familiar with the decay law. It is a statistical process. It's defined by this exponential. We have the decay constant or the decay time gives the slope, let's say the rate of the decay. Although what is mostly used is the half-life, which is simply related to the decay time by log 2. I go fast on this because I assume that you are familiar with this. Now, just let me tell you, the most important part is the most important point, the take-home message, although if you are not familiar with this, is that each specific radioisotope has a specific half-life. Okay, so from the half-life, we can identify the decay and the nucleus, and actually measuring counting the number of decays, we have information about the quantity of this contaminant in our materials. Now, a good student, what could do is to write his own code, to have this information. That's basically what I did. Now it's a code that I call Racon. I wrote this like 15 years ago. And now it's on web. If you want, you can simply click and use it. Just, I think it's self-explaining, putting some radioisotopes. You can get information. From the mass, you can get a number of decays. From the number of decays, you can get the mass and some general information on the contamination. And here, if you click also on the isotope, now there is this link. I'm just putting this link so you can bookmark this web page because you can get relative information. Here you get also information from the gamma rays that you have from the specific nuclide. Now, the question is the following. We said what we want to measure. Okay, now the question is that we have thousands of radioactive atoms. Okay, do we want to measure everything? In principle, almost everything arrived on Earth when we had the formation of the solar system of the order of 4.5 billion of years ago. We have the nucleosynthesis process that's very well known. Light elements from the Big Bang, everything else from supernovas, for example, everything arrived on Earth and was part of the beginning of this gas cloud that eventually formed our planet. Now, the point is the following, is that unfortunately for us, not everything is there. We can divide, first of all the radionuclides in two different categories. What is natural occurring? So those primordial radionuclides which are found on Earth and that existed in the current form since before the Earth was formed. And then the cosmogenic radionuclides, which are constantly produced in the atmosphere under the cosmic ray flux. Then the second category, which are the radioactive atoms, which are nucleus, which are not natural occurring, are the artificial radionuclides. Since almost 1 century, we are able to produce radionuclides, and those are called anthropogenic. Through nuclear tests or nuclear waste or accelerator, we are able to, with nuclear reaction at the accelerator or power plant, we are able to produce a lot of radionuclides. And time to time, they are released in the atmosphere. This is the abundance of the chemical elements and the Earth upper crust. You see light elements are typically more abundant. You know, we have the red ones are calcium, iron, potassium, aluminum, oxygen, and so on. Now, there are in total 252 stable nuclide, and from the prime-order radionuclides, we should just look for those which have at least an half-life of more than 10 to the 8 years. Okay, why? Because everything else which was there when the Earth was formed already decayed out. Whatever is less than 100 billion as an half-life of 100 million of years is not present. It disappeared, fortunately for us. Now, I was looking a little bit to the complete list, and I found of what is unstable and there's an half-life larger than 1/10 to the 8, and I found 34 radionuclides, which in principle should be present on Earth. Okay, what's the point? Is that we have a lower limit that is basically given by the Earth formation, but we have an upper limit, because if a radionuclide has a very long half-life of the order of 10 to the 11 or more, it's basically stable for us. It's nearly stable for us, okay? Because it doesn't show up in the as a radioisotope in the material that we extract from Earth to build our detector, okay? Those are the 34 materials, that have at least one radioisotope in this region. And this is the table of the ones which have an half-life included, between 10 to the 8 and 10 to the 11, okay? In principle, they are there, okay? The point is that there is just one which is borderline. It is here, samarium 146. But it's basically, you can see this column, the activity on Earth is very little. Okay. Then there are these four, these fantastic four: uranium-235, potassium 40, uranium-238, and thorium-232. They are, unfortunately for us, exactly in the range that we have to investigate the right half-life, and they actually show up in the activity on the Earth. Then everything above thorium starts falling in the second category. Okay, so the decay rate is very low, and in principle the activity is low, is typically unimportant for us. And these are, so there are three elements with these uranium S2 isotopes. Then there is thorium-232 and potassium-40. Now let's start with potassium-40. These are, these four elements, the two from uranium, potassium, and thorium-232 are the ones responsible for the majority of radiogenic heat on the Earth. We just saw in the previous table. That's what we basically is plotting this pie chart. Actually, potassium, unfortunately for us, is very common on Earth. If you see this chart is this plot is one of the most common element on Earth. Is lighter than uranium and thorium, so is very common on Earth. But fortunately for us, we are talking about potassium-40, so not potassium-39, which is the most stable. The stable isotope and the one which has the largest natural abundance. We have just little contamination on potassium-40. Okay, unfortunately, it's there, and this is something that we have to take into account. The main danger for us is given by it has, a decay by beta decay to calcium, but it has also an electron capture to argon-40, and then there is the excitation of the argon-40 emitting 1.46 MeV gamma ray. This line is a very strong line. In our detector is typically seen this line from potassium from the material. Actually, in the plot that I showed you before, is something that you can see always by eye, even above the whatever level of background, is this bump. So an experienced physicist can always recognize the bump given by potassium. And this is the same spectrum, a spectrum taken on surface with germanium. I had once in my lab. You see the potassium line, how is clearly above this region with all the others gammas. Okay, the good point is that it is typically easy to detect, to measure the potassium, because since it is a strong line, it does not require fancy or specific material assays method. Okay, it can be done at germanium. We will see this in the second part, but it's typically easy to assay, to measure the amount of potassium in one material. I put here for reference, for example, another line, which is here, that's thallium. That's a typical also evident, I mean, a very clear line that you have in all this kind of spectrum. If you want to get a little bit, do some exercise, you can take some, yes?
Sorry, nothing.
Ah, okay. Well, you see there are several tools that you find on web, or even now there are on Android. You can download the application. We do this kind of stuff. If you want to identify a specific line, for example, a germanium, you put the energy and it gives the list of possible isotopes. Then let's come to the other three. We say the uranium-238, 235, and thorium-232. They don't decay directly to the stable state. Each of them initiates a decay chain. In between, there are 42 radionuclides of 13 different elements. The decay chain can be identified by the mass number expressed as 4 times an appropriate integer. Okay, because every time the change, I mean, this change is produced by subsequent alpha and beta decay. The beta decay, you don't change the atomic mass. With the alpha decay, you change it by 4, you reduce it by 4. So you can identify the chain by 4 times a number and the rest of the division, basically. So we have the 4N thorium series from thorium-232, which decays to lead-208, then uranium-238 to lead-206 for N plus 2, and then the plus T, which is the actinium series. It starts with the longest lived element, which is, as we said before, uranium-235, which ends up also in lead. There is the plus 1, let's say, series, which is the Neptunian series, that fortunately for us is not relevant because the half-life of the precursor of the chain is just 2 billion of years. Okay, so as we said, we just care of everything which has an half-life above 100 million of years. So we know already that Neptunium-237 that was at beginning on Earth already decayed out, and everything now is basically bismuth 209, which now is slowly decaying with a very long half-life to thallium-205. Okay, what's the main point about the decay chain? Is that everything that there are several emitters in the chain, but most of them, different from the potassium case, do not emit detectable gamma rays. Okay, so the spectroscopy here is not sufficient. And then we need other, for this primordial radionuclide, already we need other methods to measure the contamination in specific material of this fantastic form. This is, we'll return later on this point, but let me anticipate, this is the chain, and just few of them emit gamma rays at a reasonable level. Let's say overall in the uranium-238, 232 chain, we have a factor 2 gamma rate with respect to the alpha decay. So for uranium decay, we have, and thorium decay, we have in the entire chain the probability that 2 gammas are emitted. So just few lines actually can be measured. For example, this is the case. You see here a nuclide, the energy of the line, and the emission probability. Just, you know, very low emission probability, very low energy means that it's very difficult to measure this line. You can, in this case, for example, you can nicely measure lead-214, but it's very difficult to measure thorium-234 in this chain. And that's the same for uranium-235 chain. And thorium chain. What else? I mean, not only the gammas are important for our experiment. We see at the beginning, setting the stage, that also there are emission of gammas and betas, which somehow can affect our experiment. And that this is the case. We have emission of several alphas, much more than gammas in the decay chain, and beta at the same time. Alpha emitters, which are very important, are typically polonium with all its isotopes. And this is, for example, we won't go through the details, but just to give you the idea, it's a fundamental aspect, for example, for those of you who do dark matter investigation. You know that neutrons are a big problem for dark matter because it can produce nuclear recoils in the region of interest of the WIMP search. Basically, a neutron can be hit by an alpha, can emit in an alpha N reaction a neutron, and this poses a very important threat to this investigation. Okay, from the alpha, although neutrons are not directly or minimally produced by the prime order radionuclides, just by the small fission that uranium-238 can have, you can produce neutrons indirectly by alpha N reaction. Okay. The yield is typically depends on the density of the contaminants, in this case, for example, uranium and thorium, the density of the material, and then you have to integrate the cross-section between the alpha 0 and the alpha energy, the cross-section of the alpha N reaction, divided by the stopping power of the alpha of the materials. Okay, the problem for this calculation is that the cross-section are not very well known. This is an example of a very well-known cross-section. I mean, that's for beryllium-9. It's something that maybe you have heard, because the alpha americium beryllium source is a typical neutron source, and neutrons are produced associating an alpha emitter, the americium, with beryllium, which has a high cross section for alpha N reaction. Okay, so this is a specific aspect just to give you the idea that not only the gammas are important for this investigation. You have to calculate, based on the alpha decay, all the neutrons, for example, that are emitted. There is a new code now. Let me advertise this, which can be used for this calculation. It's based on Gen4. If you are working in this business, you can use it. That's an example of the calculation of the spectrum of the neutron produced by uranium-thorium decay in aluminum fused silica, or PTFE, which are common material used for low background experiment. And those alpha N, those contamination and alpha N neutrons, I mean, uranium-thorium contamination in the rock, are also the main source for the neutrons emitted from the rock. That's an example. You know, even given going underground with your experiment, you still have an environmental radiation, gammas and neutrons from the rock. Neutrons are produced precisely from the rock, are produced precisely from the uranium-thorium contamination in the rock and alpha N reaction. Now, there is another important aspect. So what about this chain? Okay, for potassium, we said that we can measure it directly. Okay, uranium and thorium would be what we can measure. It would be enough to measure just one element in the chain. Can we measure just uranium and we are done? Unfortunately not. That's the answer. Because there is an important point, is that the chain could be in equilibrium or not. What is the equilibrium? The equilibrium is typically means that the activities of the parent nucleus in the chain and all the daughters are the same. Okay, so in this case, it would be enough to measure just one element of the chain. Then we will get the activity of the entire chain. But the point is that, okay, we have to measure, and we are not even sure that the equilibrium is conserved. Why? Because it can be broken, and then in this case, it's typically done when the half-life of the parent is shorter than the daughter. So if the half-life of the parent is longer than the daughter, you typically have the equilibrium. But if it is shorter, you don't have the equilibrium. Okay. The consequence of this that you have to assay typically the entire chain. I won't go in details about the rules of the law of the equilibriums. That's typically that it is expressed through the Bethenham equation. It gives you the rate of the decay of the nucleus as function of the decay rate of the nuclei and its parent. Okay, this is in case when you have the decay of the parent nucleus, you don't have daughter. When you have some activity of the daughter, that's taken into account in this other equation. Okay. The take-home message is that when you have this chain, you have parent and daughters at the same time, and you have to assay the entire chain. There is one specific aspect which is related to the chain of the primordial radionuclide, which is the secular equilibrium. Okay, we said the equilibrium, we have the same activity, and then the decay time is typically of the chain is driven by the element which the half-life, the longer half-life. Okay, because the activity is the same. So all the elements in the chain, longer or shorter, are driven by the elements with the larger half-life. Okay, we say secular equilibrium, which is actually a specific case of the equilibrium when the half-life of the parent is very long and the half-life of the daughter is negligible, shorter or negligible with respect to the parent. That's obviously the case of the uranium and thorium change, because the half-life is 1 billion of years. So in this specific case, what happens that a daughter nuclide decays at the same rate at which it is produced. So in this case, the number of atoms present in the sample remain constant. Okay, you can simply see this plot over here. That's a calculation that I did for fun, just using the Racomb code, the code that I presented before. You can get per ton of uranium-238, you can get, given the secular equilibrium, the mass of each single daughter of the uranium. Okay, the most important one is uranium-234, and then there is thorium, radium, and polonium. This is obviously driven by the specific half-life of each daughter. The one which has the number of larger number of elements are the ones which has the larger half-life. Now the question is, okay, we say the equilibrium is not guaranteed that we have in the chain. Actually, we can say something a little bit more specific. The equilibrium in the chain specific for the uranium is rarely achieved in most of near surface geological environment. Okay. I mean, it's hard to say now why this is the case. I can tell you that empirically measuring assaying the entire chain of uranium-238, I have to say that it's very rare that we measure the same activity in different parts of the chain. As general concept, we can say, I will talk later about radon, but I mean, not only just by radon emanation, the chain can be broken, just by chemical, natural or artificial processes that can happen during the extraction or production of the material, which can deplete or enrich the material, the specific material, or of a specific component. Okay, that's an example that I wrote here. We can simply read this just as a sample of the way the chain can be broken. If the uranium is dissolved from a primary uranium-bearing mineral by oxidation, the remaining radionuclide of the 238 series will be supported by its most long-lived radionuclide, which is 230 thorium-230. Okay, then the uranium can be eliminated, and then the decay chain is driven by thorium. Okay, there is in the upper part just the one which is the leftover from the uranium, but the main contamination will be below thorium. Okay, and then the time to reattain the equilibrium, it would be, I mean, very long, because still thorium has a very long half-life of the order of 75,000 years. Okay, so that's an example of what we said, what is called transient, or I would say usual equilibrium. With that's a specific example of the activity of equilibrium between two components, lead-210 and polonium-210. You see there is the decay Okay, that's in time years, the decay of the lead-210, and then we start the activity of polonium, which is a decay product of lead-210, starts building up and then follows the decay of polonium. Okay, this case of no equilibrium is very clear, since we start building this, that it's not a specific example, it could be whatever, there is plenty of example. And then you start building the activity of the other element, which decays with this long half-life, longer than the parent nucleus. And then there is the secular equilibrium, which I just said, an example of uranium-238 with radio-226. That's the activity, decays per year of the uranium, whatever sample. You see that we start building. Check the time scale. Look, be careful of the time scale. We are talking about tens of thousands of years. We start building the activity of the daughter, and the activity remains stable. Okay, and the number of atoms as well. I actually not a big fan of this specification. Basically, secular equilibrium is a specific case. We can talk about equilibrium in general. Secular equilibrium is simply related to the fact that the half-life is so long that for a realistic time that we can consider, there is basically very little variation. But on a very long time scale, the secular equilibrium can be considered as a normal equilibrium. With the decay of the uranium, at the end, we always end up with the lead. Second example, that we can break the equilibrium, so we can measure different. We have to measure. We don't have the same activity in different parts of the chain. The equilibrium can be broken due to the radon emanation. This is a test I did 10 years ago. At PSI was producing a thorium source with specific characteristic. Anyway, part of this test was foreseen the production, the heating of the sample in a crucible at higher temperature. Okay, so heating the sample, we get rid of radon, okay, which is released in the air. So we break the chain at this point. And that's an example of the spectra that we take of this calibration source that we were producing with these specific techniques at different time. This was before, okay, the production of this treatment. And you see two lines from two gamma rays in this chain, 241 from radon, which is before radio, which is before radon, and this from lead-212, which is after the radon. Okay, you see that what you expect, the ratio between these two lines is 10.6, and that's what you measure before the treatment. Right after the treatment, you see that you break the chain. Because the radon has been released, so this part has been for a while depleted, this part of the chain. Then what else? I mean, the point is that the half-life for radon-220 is very short. So after a little while, you recover this part, okay? Because you keep producing radon from the radium decay, and then after 2 months, you recover the ratio between the two lines, which was before the treatment, and that is what you expect. Okay, so the chain now is in equilibrium again. Typically, for this kind of measurements, for the radio purity point of view, we split the chain in 3 parts, which are the 3, let's say, typical way in which the chain can be split. So there is the upper part from uranium to thorium, then the one which is below radium-226, and the one that is below the lead-210. Okay, you can see this is simply based on the half-life, because here you are decreasing the half-life, so this is typically in equilibrium because the daughter has an half-life which is less than the parent. That's also the case in this region from the 1,000 years to microsecond. And that's also, you can split the chain here because you have problem from microsecond to years, but then you have years, days, and then stable to polonium. Okay, so we divide the chain in 3 parts, upper, middle, and lower. That's for uranium, that's for thorium. The upper part is just thorium. And then we have from radium to thorium-228, and then below radium 224. Okay, we said that that's for the cosmogenic, for the natural occurring radioisotopes, we had primordial and cosmogenic. Those are produced, those are natural occurring because we are not producing it. They are already on Earth. So the difference that, as we said, primordial have been produced before the Earth was formed in this galactic disk of gas, primordial galactic disk of gas, which form our solar system. But then that's not only the component that we have to care of, because we are, in principle, there are radionuclides which are constantly produced on Earth under the action of the cosmic rays. Okay, these typically this process produces lighter elements. The point is that those are much more, and they are half-lives can change greatly. Okay, there are not just 4 of them; there are many of them, and the cosmogenic isotopes that we find in a material typically depend on the specific material. Those are, I mean, just as general information. They can, I mean, those radioisotopes can be either produced in the atmosphere when we have this hadronic shower, or even at the ground, because I mean, we have the secondary particle from cosmic ray, the muons, which reach the Earth. So they can be produced, for example, by spallation on the Earth crust. An example of production atmosphere is the production of carbon-14 or tritium. Since which are basically done, since the atmosphere is basically made of nitrogen, so by neutron capture is something that you can likely produce. Since the intensity of the cosmic radiation is long-term constant, the production of cosmogenic radionuclides is rather constant. However, there is a great variation at different heights of the atmosphere and different latitudes. This is a list of other important radionuclides. We will talk also a little bit more in details later. Important aspect for the material radio purity concerning the cosmogenic. You have to be careful because transportation in air of the material that you have to use to build your detector is dangerous because of the hadronic component. So if you send a material by flight from I mean, to your underground laboratory, that can be activated, and you have either calculate the activation or measure it, the activation that you have in your material before making sure that this material is good for your experiment. An example is the spallation production of germanium-68. Because high energy cosmic ray can produce through spallation reaction more nucleus, as we said. So in a germanium, you can have this reaction, and you produce germanium-68 with an half-life 270 days. Okay, so you have to wait until your germanium crystal, for example, cools down, and you can use it, for example, for material screening. This is also the reason this reaction of the radioactivity naturally found of 0.3 millibecquerel per kilogram in germanium crystal on the surface. Then after that, you have to be you have to store the material underground in order to prevent, once you have the detector obviously has been the material has been delivered, you have to store it underground to allow the cooling down and to prevent the further production of cosmogenic in your material. Actually, everything which materials which are typically extracted underground, this is the case for argon. Probably you already heard about this during these days. Okay, this the argon extracted underground, for example, it doesn't have argon-39, which is cosmogenically produced in the argon in the atmosphere. And it's something that you clearly see in your argon detector using the argon distillated from the air. So as I said, the list of isotopes is very long. These are just examples. I have a reference here that you can use with a more complete discussion. In copper, typically you have, you know, these are a lower mass or mass comparable with the material that is exposed on surface on cosmic rays. On copper, we typically have cobalt 60. On stainless steel, we have again cobalt, manganese 54. But the take-home message here is that it's hard to say precisely to have a list of contaminants. You know by experience what are in principle the most important ones. You can do your calculation. Okay, for example, if your material is being shipped by flight, but the main important point is to measure the gamma activity in your sample, identify the cosmogenics. The last, and this is the end of the first part, the last subset of nuclides are the subset of radionuclides are the artificially radionuclides. Okay, as I said before, it's since 1 century we start producing artificial radionuclides. This is done with nuclear weapons. Exploding the nuclear energy in general with nuclear power plant. We can produce actually at the accelerator a lot of radioisotopes which are good or necessary for the medical physics, medical application. Okay, but what's the problem for us? Okay, it's just the fact that time to time, by chance, these artificially produced radioisotopes are released in the atmosphere. This has been done during the test of the nuclear bombs during the 50s, 60s, which released a lot of radioactivity in air, or during the accident of the power plants, Chernobyl, Fukushima, and so on. The level of radioactivity that we want to measure also is very sensitive to this kind of accident. Okay, that's something that we found in our detectors. Example is cesium-137, which is a typical fission product along with iodine, xenon, and strontium, which is released in the atmosphere, for example, during the Chernobyl accident. And we know that we have on the order of several kilobecquerel of contamination on surface per square meter in East Europe, just given by the Chernobyl disaster. Okay, so that's something that typically shows up in our detector, this kind of contamination. Another example is krypton-85. Is one again is in the mass range of the typically of the isotopes which are typically produced during the after the fission. Okay, this is found in the nuclear rods, and it's very typical product of the nuclear power plant. Okay, so just the accident of the Fukushima, the accident of the power plant in Fukushima released an estimated amount of between 44 and 84 petabecquerel in the atmosphere, while the normal concentration due to cosmic ray in atmosphere is a fraction of the order 0.09 petabecquerel. So we are several orders of magnitude above the natural concentration, and probably this is not even, not just Fukushima is the main source of krypton-85 or the nuclear accident. Just intentionally, let's say, some krypton is released time to time during the reprocessing on the nuclear waste. This gas is released in the atmosphere. That's an example. This is what I showed you before from Radon, from darkside 20K, the background spectra. You see that there is krypton-85 over here. It's actually even above the argon-39 contamination over here. And as I said, this is to demonstrate that even the artificial radioisotopes are typically found in our detector. Okay, there is just one more point I would like to stress. That's radon. I think you are more or less familiar with the concept. Okay, we just introduced the natural decay chain. We have in the middle.
Sorry, Roberta.
Yes.
at a certain point, in few minutes, I think it would be fine to ask for questions.
Yes.
In case. And I want to ask you if this is at which point you are. I mean, when can I interrupt you here, or you prefer?
Yes, 2 minutes more, because I just
fine.
just split it to have the first half more or less.
Of
in this
course.
part.
Okay, fine.
Oops, sorry. Okay, we have in this radon decay chain, we have radon at a certain point. We just introduced, I showed the concept of we discussed the concept of the radon emanation. And this is also something that a problem that we have to address in our assay measurement. Why it is a problem? Because it's not in the material, but somehow it can be, I mean, it is in the air. That's something that I think is very clear to everybody, the fact that we have a constant emanation of radon. So it's a typical contaminants in air. But the point is that when radon decays, it produces the radon daughters. For instance, for example, lead-210, which is very long, it has a very long half-life, and this lead-210 can be deposited on the surface of the material. Okay, so if you are not careful during the production process of the materials for the component for your detector, if you don't take this into account, you end up with a surface contamination. So this is another type of contamination which is not in the bulk of your material. It's not given by the fact the material is at the origin contaminated, but it can be contaminated on the surface by the radon decay. Okay, because the polonium decay basically sticks on the radon decays, and the lead-210 which is produced sticks on the surface and stays there for the entire life of the experiment, because its half-life is 22 years. For example, for dark matter, this is an important problem, because one of the decay of the lead-210 is polonium-210, and polonium-210 is an alpha emitter. It could be an important source of alpha and neutrons. Now, this contamination strictly depends on the activity of the radon in air. This is a plot of the activity of radon measured in the becquerel per cubic meter in Gran Sasso, in Canfranc laboratory at the beginning of when the lab basically starts. You see that there is a huge variation of this contamination, and even that the contamination can be widely different in different parts of the laboratory. Okay, that's a bit the contrary of the cosmogenics. When the cosmogenics is dangerous above ground and safe below ground, underground, for the radon, it is the opposite. Typically above ground, we have a realistic level of a few becquerels or 10 becquerels per cubic meter. Underground, this value could be orders of magnitude higher. That's an example of what I say, just how there is this equilibrium between lead-210 and polonium-210 with the production of polonium from the original radon decay. Okay, I think we can stop here, because now we go to the second part, which is how can we measure it.
Okay, very well. Thanks, Roberto. It was very interesting indeed, and very clear indeed, but a lot of information for our students. And so I have seen that there is a question in the chat. Maybe it's from Sartak Shudari. Maybe he wants to tell you by speaking.
Yeah, actually, I have two questions. First is about the secular equilibrium. So I think I kind of lost my train of thought there, but so what I understand is there is a parent nuclei which is decomposing into daughter nuclei, and then daughter nuclei is also decomposing, but the rate of decomposition are so that the daughter nuclei remains same in the amount. But that is, I mean, why does that matter in our conversation? Because decay is still happening, right? So radio, other decomposition products will still be there in the material, right?
Yeah, I mean, let me tell you this. Maybe this it could be easier. So if you just look at the chain, okay. So what you have in the secular equilibrium is that the activity is the same. Okay, that's the general concept of the equilibrium. But in the secular equilibrium, every single components of the chain is decays, and it is produced at the same rate. So what is stable is the total amount of materials. Obviously, that's why I see it a little bit, it's a bit misleading, because on the very long term, obviously you never have the secular equilibrium, because the uranium is always decaying out, and the lead is stable, so is always enriching, okay? But for short, for limited amount of time, each decay, you know, the decay of radon one decay of radon is compensated by the decay of radium, okay? So what you get is that the activity is stable, and you have a constant amount of contaminants in your materials.
Okay, but my question is, even though, so that is fine. I understood, let's say for radon,
I mean, sorry, let me add this. Maybe it's
okay.
a final statement. If you consider the decay on time scale of billion of years, you will just see on hundreds of billion of years, you will just see the uranium decaying exponentially to lead to 10, lead to 6 in the case of uranium-238. Okay.
Yes, exactly. And but while all these processes are happening, so however the parent is decaying to the daughter nuclei, we are getting all other products, right? Whether it is alpha particle or beta particles, so they will still contribute to our background, right?
Yes, you have everything at the same time. And that's a bit the message that I wanted to pass. Maybe we can see this slide. It was here. You know that the amount of material that you have here, okay, you have everything at the same time. When you have a new uranium, 1 ton of uranium extracted from the earth crust, you know that you have all the other things at the same time.
Understood. May I go to the second question? It's a short one, where you said like by heating the material, you can get rid of the radon. It will degas. My question is, but that will only happen from the surface or right below the surface, right? Or if the radon is present in the deeper layers, that wouldn't degas, right?
You mean deeper layer of the sample, the material that you want to use to build your detector? The
Yes,
layer, you mean the layer of the material?
Yes.
Yeah, I mean, in principle, so you have to consider this. This is a more technical aspect, but it's a key ingredient to answer to your question. The point is that radon is obviously a noble gas. It has quite high mobility in your material. Okay, it diffuses. So it's not like everything else. It's a gas and it's noble. Okay. Radon actually can migrate from the center to the surface. It's true that in order to be emitted before decaying out, in the case of radon-222, you know, the half-life is 3.8 days. Okay. Before, or even, I mean, seconds, or for the others. In order to be emitted before decaying, this radon should to migrate to the surface. So it is typically emitted from the, let's say, outer skin of the sample. Although consider that this skin is not so thin, because the let's say radon could travel within your material. That's basically what actually happens, because you don't deplete the radon just on the surface. You redistribute the radon inside your material.
Okay, so you are saying you choose the um, so my understanding is once you have the material, you will do some, like you have to form it into some shape, and you choose that thickness not too thick, so that from the below you can also get, from the center you can also get.
The strategy, let's say for radon, is the following: is that in principle, it would be better for all the aspects related to the radon, it would be better to clean the surface of the material. There are specific methods to clean the surface of the material to get rid of the radon daughters, which were deposited on it, and then to protect the surface of the material with, for example, if you have to build something which is in touch with your active volume, to clean, to cover this surface with a material which is not transparent to radon. Let's say something that protects the active volume of your detector against the radon diffusion. Does this answer to your question?
I'm not sure actually.
I would suggest that
Yeah,
so
sure.
we have the discussion session at 6:30 dedicated to longer explanation if something is not clear.
Yeah.
Maybe now we can stick to short questions and then let Roberto moving on.
Yeah, in fact, I have the impression that Sartak wants really to go deeper in this discussion, and that's fine.
Sure.
And it can be done, of course, I agree, afterwards during the discussion session. And now let's see if somebody else, if there's some other question, short question, so that afterwards we can complete the presentation. Any question? Okay, no questions so at the moment. So please, Roberto, we can restart with the presentation.
Okay, how can we measure it? Again, summary of the first part. We say that we have, we don't have to spot all the possible radionuclides from the nuclide chart. Okay, there are specific things that we have to look for. Those are the primordials, and there are, in this case, potassium, two isotopes of the uranium, and then thorium-232, cosmogenic, which are mostly gamma emitters specific in the materials, and then some anthropogenic emitters. Okay, so how do we measure it? First of all, orders of magnitude. Okay, we typically measure the contamination in becquerel per kilogram or millibecquerel per kilogram, or ppb. There is this conversion factor. In general terms, it's there. In general terms, we can say that the contamination of becquerel per kilogram is quite high. But let me make this statement that this is not in absolute terms, okay? Because I mean, it's hard to say that this material is always good and another material is always bad. There are materials which are typically good and typically bad, but it depends on what you want to do. Okay, if you want to put I don't know, a sensor which has FR4 close to your detector, this is typically bad, but it depends on the level of background that it produced, the total amount of mass, and so on. So it has a specific case. It has to go. It has to be discussed case by case. But in general terms, let's say a material which is of the order of becquerel per kilogram it has a contamination which is not that good for us. Example, just to give you an idea, everything that we are dealing with is this order of magnitude more than becquerels per kilogram. One banana is, there is a lot of potassium in the banana. I did this calculation. The contamination of one banana, which is 200 grams, more or less, it's of the order of 100 becquerels per kilogram. Or even the human body. I mean, again, potassium is very common, not only on Earth, it's also common in our body. You can do this simple calculation. I go a bit faster now. You can go through this information, but it produces potassium in our body at the order of 4.2 kilobecquerel. So this gives you a contamination of 60 becquerel per kilogram just from our body. That even without taking into account, for example, carbon-14, which is also the second most abundant emission in our body. Okay, many of the, I mean, if you are curious, you can see some typical results on this database. It is radiopurity.org. There is a lot of information. The point is that as in a little bit everything in this field, you have to have a bit experience in order to dig out the relevant information to make the right conclusion. Okay, common assay techniques. How do we measure the contamination of our materials? We will be discussing these typical techniques. Gamma counting with germanium crystal, that I think is the most popular. Maybe some of you are familiar with this technique already. Then there is mass spectroscopy, and there are several types of mass spectroscopy. I'm going to just say something about ICP-MS, glow discharge, and the laser ablation, then neutron activation analysis, emission spectroscopy, and radiochemical methods. This part is a bit technical, okay, because there are it's a further step into technical aspects. I'm trying to give you the general concept, evidencing always the take-home message. If you have questions, we can discuss this later. But I mean, the point is that don't be afraid. Try to get just the take-home message. Okay. So gamma spectroscopy, I mentioned during the first part, this is a typical technique. It's actually very good for potassium since it is so abundant, and it can spot all the relevant cosmogenic gamma emitters cosmogenically produced. The idea is to detect the gamma rays with an high purity germanium crystal in the range 100 keV, 10 MeV. It is a non-destructive technique, so this is important because sometimes the samples is valuable. You want to measure the activity of the samples, but you still need it. And that's good because with germanium you measure it and then you get the sample back in the same shape. Now, why do we use germanium? I think the concept is very clear. There is probably no doubt over this, just measuring the gammas. Why do we use germanium? Maybe that's something interesting for you. So the reason is that we can build, it's a semiconductor detector, and is one of the best, probably, the best of this type that in terms of the energy resolution. That's extremely important, the energy resolution, when you want to identify gamma lines. We saw the gamma spectrum before. Obviously, if their energy resolution get worse, you get, it's much more difficult to quantitatively measure the activity of this gamma line. Okay, that's a comparison between germanium and other crystal. Germanium is very good because it has a very small band gap between the conduction and valence band. It has the lowest energy necessary to produce electron and hole pairs, and the mobility on the electrons and the holes is very fast. And it also has an high density, which is very important in order to measure the full energy peak of the lines, because the crystal has to be massive to stop the gammas. Now, just a drawback about this nice feature of the germanium is the fact that since the band gap is so small, it's not possible to operate the germanium at room temperature. It has to be can be operated just at cryogenic temperature. It's typically operated in liquid nitrogen. And then all the rest of the material around the germanium should be as low Z as possible here to reduce the photon scatter. Obviously, in order to enhance the efficiency of your detection, you should put very little material between your sample and the crystal. Okay, just a few general information. This is detectors could be a p-type for, they are doped with the p-type or n-type for positive accept or negative donor impurities in your detector. And it has a thin layer of very high, with very high dopant concentration, which make the contact for your crystal. And it is powered with a reverse bias junction. This means that the positive voltage is connected to negative type of the semiconductor. So this is let's say a design which evolved along the years, and now is very typical. It allows to really measure with very high efficiency the lines in the range of 100 keV, a few MeV. Although be careful that when you want to do the analysis, don't take a line. I mean, you have to be experienced in order to really understand the source of a specific line. Just one line, for example, if you are, let's say, keeping in mind just the basic of the interaction of radiation with matter, can produce several lines. Beside the full energy peak, you can have the Compton tail, the single escape peak, and the double escape peak. You know, there is a bit of experience that is necessary to measure the activity using the germanium. That's about the production. I think we can skip this. This is the typical assembly of germanium detector. As I said, there is it has to be cool. There is a cold finger with germanium on top, and there is in a typical assembly just a thin end cap, and then you can put in principle the source just on top of this cylinder. Pictures of germanium I used once in my lab. One of the recent development in this field is the production of the well type germanium. Those are all P types germanium. And the reason is that these, with respect to the coaxial typical, let's say, crystal geometry, they have a hole inside. So you can put small sources inside the crystal. Okay, in this sense, you will be able to measure nearly 100% of the photons emitted, or I mean, close to 100% of the photons will interact with the germanium. Just a reduction of the efficiency is given by the few photons which may eventually escape, or the material which is played in the middle. These are pictures of the operation of a germanium which is placed underground. That's from Canfranc. You see, each single measurement is a little experiment. You have to put the source on the germanium. The germanium is inside the lead shield in order to stop the external radiation. And then within the lead shield, there is a very clean copper shield, high purity copper shield, which is meant to stop the remaining radiation from the lead itself. Okay. One important point is that all the analysis is not trivial, also because you always, for each sample, you need a Monte Carlo. Okay, because you have to parameterize, simulate the geometry of your sample that you put in the on the detector, and extract the variation of the efficiency for the detection of the gamma rays as a function of the energy. Okay, this is one of the typical low background facilities which are installed in almost all the underground labs. This is at Canfranc in Spain. There are similar facilities in Snow Lab, Bulby in UK, LNGS obviously, and so on. Okay, in this specific facility there are 7 high purity germanium crystal. The mass typically of the crystal is of the order of 2 kilograms. This is a few information about the germanium, just to give you an idea, still staying on the crystal LSC. This is a well detector, that's the best one. I mean, the most interesting part that I can evidence more than the mass is the background that those detectors have. You know, in order to measure the gamma light from the sample, actually from radio pure sample, you need an intrinsic, very low intrinsic background. So the contamination of the germanium itself is an important parameter. And we can reach, with this technology, you know, with this high purity germanium, we can reach levels of less than 1 count per kilogram per day. That's amazing from my point of view. These are analysis of samples that you get from the assay with germanium. A list of sometimes is very detailed, sometimes not. It depends also on the facility which actually assay the sample. This is a comparison of two different acrylic samples in two different facilities. Okay, the message you can, I mean, that's you can see the units. That's a take-home message for what I said before. For good materials, you should be at the order of millibecquerel per kilogram. An important aspect that several times, I mean, you won't measure a specific line, but you just set a limit. Okay, that's typically the case because you want to assay new materials. I mean, good materials. And in order to assay good materials, the line shouldn't be evident, okay? Because if you are able to measure clearly the line, typically it's quite bad. So the case that you have just limits on the line is actually one of the typical cases. In this case, for example, this acrylic is good. You even have a limit on potassium. So for this other case, you have limits on everything else, but a strong potassium line. So figure on merit of this technology. It's the best technology to assay gamma emitters. And certainly it's very nice technology, first of all, for potassium and cosmogenics. And for the uranium and thorium chain, just for the middle chain, where the most relevant gamma emitters are located. It requires a very simple, relatively simple sample preparation. It's not that difficult. It's not not destructive technique, as we said before. It is we can reach very good sensitivity of the order of millibecquerel or less. Although it has to be stated that this is one of the limitations, that this sensitivity depends on the mass of the sample. Okay, this is not suitable for small sample. Since we want to measure gamma rays, we need quite some mass of the material that we want to measure in order to have a significant, I mean, to have a line above the background of the detector. If you want to assay, for example, resistor, SMD resistor for the electronic components of your detector, you need quite some, I mean, many thousands of resistors, okay, in order to have a mass which is which can give a realistic measurement, a good measurement in terms of radiopurity with germanium. It is, I mean, the operation is a bit difficult at germanium in the sense that it has to be very stable in controlled environment, also of temperature, humidity, and so on. It is only sensitive to gamma emitters. It doesn't measure anything else which doesn't emit gamma. Several weeks are typically necessary to assay the sample. You have a sample. If the sample is, if you are able to assay the sample in a few days or 1 week, this means the sample is typically heavily contaminated, okay? And it's typically not good for your experiment. In order to assay good samples like acrylic, like copper, you know, the materials which are typically used for this kind of activity, you need of the order of 3-4 weeks or even more than a month in order to get a good sensitivity. And you need a detailed Monte Carlo simulation for each sample that you measure. Now let's move to mass spectroscopy. Okay, we said at the beginning that's what we need in order to have to do our job, to fulfill the goals that we have to achieve the characterization, the entire characterization of the samples and then of our detector. We have to use multiple techniques. Why? Because germanium, for example, is only able to assay a specific radiocontamination and only a part of the decay chain. What do we do with the rest? For example, we can use mass spectroscopy that can be used in parallel to the germanium counting. We are going, I mean, there are several techniques. I'm going to show you some slides just of the first part, which is the inductive cold plasma mass spectroscopy, then the glow discharge mass spectroscopy, and then what I think is a bit the future in this field, which is the laser ablation mass spectroscopy. Mass spectroscopy, it allows the determination of elements with atomic mass between 7 and 250. I will tell you later why we cannot go below 7. It can determine the concentration of the contaminants very low level for almost every kind of sample, reaching a resolution of picogram per liter. We can say that is in the range of the germanium. We can reach of the order of PPT or even sub-PPT level, but that just in specific case. It is a destructive analysis. So it needs a complicated sample digestion because we need to insert liquid in our spectrometer. So we cannot assay solid in solid form. We have to dissolve it. In comparison with other mass spectroscopy techniques, is advantageous because everything is done in liquid solution at room temperature, at normal pressure, and the analysis is very fast. What's the idea? Sorry, this is a bit covered. I didn't notice this. This is a typical layout of the detector. There is a plasma torch here where we introduce the sample, and the plasma is generated in argon atmosphere. So everything is turned to plasma. The reason why we cannot go below 7 mass unit is the fact that since this is done in a normal atmosphere, the typical elements which are present in the atmosphere could, interfere actually with the measurement in the low mass region. So at the end, you can measure something above 10, but this is in our field, this is typically just used for the high mass measurement, for instance, uranium and thorium. At the same time, we cannot actually measure potassium because potassium that we want to measure is 40, and 40 is also argon, which is one of the gas used for this measurement. It is introduced to drive the sample in the measurement part. Okay, so this, let's say, potassium 40 measurement is kind of shadowed by the argon injection in the system, so we cannot measure it. Then there is let's say, the material after the full ionization of the nuclide is transported to the low pressure part and then is analyzed, with the mass spectrometer in order to measure the mass of the material. Basically, this is done with 3 different techniques. One is the quadrupole, that is the most used. One is the double focus sector with the electric and magnetic field, which is the most sensitive one and most expensive. Sometimes there are also spectrometer, which is the time of flight in an electric field. So these are the components that we need: an ion source, the extraction region, the low pressure interface, and this analyzer. My experience is that with this kind of assays that it's very, very simple, the measurement. Basically, everything is already included in the detector. You just insert your source, and then you already get the number of atoms that are present in the plasma that you are assaying. That's an example of the results that you get directly on the monitor. These are calibration curves that you get with the calibration samples that you use, which are solution with known amount of uranium and thorium. So you can easily calibrate this scale in terms of counts per second, convert into ppb of the material. So the measurement, it takes probably less than 1 day. I would say even a few hours. This is an example of the low part region, but as I said, we are mostly interested in the uranium and thorium with this technique. Now, why don't we assay all the rest? Okay, we said, okay, we are in we want to measure the high mass part. Okay, why don't we measure up to lead with this kind of assay? That's would be the ideal case, because we can then measure the entire chain with the same technique and the same machine. And this is still in the high part region. But why do we just measure uranium or thorium? The reason is this, okay? Just measuring the mass that we have, considering more or less the equilibrium in the chain. The uranium is the one which is present with higher mass. Here we don't detect the activity. Here we detect the mass, okay? And the activity can be the same or nearly the same, or can be, let's say, similar in the chain, but the number of atoms is much smaller, okay? So we don't have a technique which is able to go through the chain, assaying the different part of the chain. we can measure just atoms in this range. Okay, this is the number of atoms and this is the total mass. That's what I showed you before also. The mass for a ton of mineral of uranium extracted from the surface, and then you see that everything else has a much lower contamination in terms of number of atoms. So this concentration is too low for whatever kind of technique. Now, I say that this is ideal, at least to measure uranium and thorium. That's not the entire story, because there is, unfortunately for us, the bad part of the story, that is the sample digestion. We can insert in this machine just liquid sample, okay, in order to turn them to plasma. Now, there is an important part that is, I mean, within this technique, which is the preparation of the sample. So we have to dissolve the sample. Typically, this can be easy for some kind of sample. For copper, I would say that is easy. You just put copper in hydrofluoric acid, you wait a little bit, and then it dissolves totally, the copper. Okay, and then you can assay it. That, I would say the assay of copper with this technique would be on the order of a couple of days, not more, much faster certainly than germanium. The point is that not everything can be easily dissolved. So beside the acid dissolution, which can be with low temperature or higher temperature, there are, I mean, maybe technical details that we can discuss later if you want. There are other techniques to dissolve the sample, which are not easily, they cannot be easily dissolved in acid, which is the dry ashing. So we simply heat it up at the range that the sample basically release the most, almost the lightest components of the sample basically evaporate, and then we end up with uranium and thorium in our crucible. And that can be later injected in the spectrometer to be assayed. This is typically used for organic matter in order to break, the carbon bonds. You heat it up, you get rid of the carbon, which I mean, it produces CO2, it goes away, and then you ended up with uranium and thorium, which stays in your sample. These are example of results that you get. Is here is totally different. Okay, that's for a stainless steel sample. The interpretation of the analysis results is quite straightforward. There is almost no discussion, differently than the germanium assay, because you have uranium and thorium concentration. These are just different tests that have been assayed. You know, there is just a bit variation between the different tests, but that enters in the statistical error that you get. But there is an important part, which is the most difficult, which is the sample preparation, actually, and that's maybe when you get the report, typically 80% of the part is just the description of the sample separation, which is necessary in order to support quantitatively the results that are reported here. So, pros and cons of this technology. It gives a fast analytical, it is a fast analytical technique for simultaneous determination of ultra trace element in liquid solution at very low level. You can reach a very good sensitivity, probably better than the one, in ideal case, better than the one you can get with germanium, even in the uranium chain. Little amount of material is needed. And if the spectrometer is sensitive enough, you don't only measure an element, you measure the isotope, okay, because it has a different mass. You measure the mass, you can get, you can measure the natural abundance of the element that you have in your material, okay, with between the different isotopes. On the contrary, it is a destructive analysis. If the sample is valuable for you, you cannot just do this because it will be dissolved and disappear. The sample separation is very difficult from my point of view, and it takes quite some time for specific material. It cannot measure potassium-40, and there are other specific aspects which are the molecular ion interference, but this is experienced analysts could really overcome this problem. just 2 words about the glow discharge mass. I don't want to go through the details of this technique. Let me just stress this point, simply because the ICP-MS is probably the most popular and most sensitive technique nowadays. The only advantage that has the glow discharge mass that you can use solid samples. So you skip the part of the digestion of the sample. It is basically a different way to produce this plasma here. It doesn't have this torch. At the beginning, there is just argon atoms, which, let's say, are sputtered on the, are eating the sample. So the sputter neutral particles from the samples are then driven in the measurement part. Okay, that's a way to get some atoms from this material. The only interesting point from my point of view is that you can do this if you are really not able or you don't want to dissolve the sample. Okay, but anyway, that's not probably the best solution, because since I would still say recently a new technique was proposed and is becoming very popular, which is the laser ablation ICP-MS. What's the idea? Still, let's try to get rid of the most difficult part, okay, which is the dissolution of the sample. We want to get the uranium and thorium content on this, and then we say that for ICP-MS we have to dissolve. Another way to get to overcome the acid of the preparation is simply to use a laser now, which are so fancy, so powerful, which can easily ablate the surface of the material. So the concept based on underlying this technique is that the chemical preparation is replaced by using a laser in ablation mode. We avoid the time-consuming sample preparation because this is done in time scale of minutes, and there is a small risk of sample contamination. So it's a super clean technique, very good, very sensitive, because the measurement part is the same, like the ICP-MS. We have a mass spectrometer, you just get some atoms from here, you introduce in this mass spectrometer, and then you measure it with the same resolution of the ICP-MS. Now it's getting more popular because we have fancy laser, as I said before, and in principle, with very short laser pulse, we can minimize problems that they had at the beginning when they proposed this technique, which is the thermal effect, some systematic effect about the power of the laser and the heating up of the material. With short pulse, let's say, we can really control the operation of the laser. These are examples of results of the laser ablation technique. The interesting part is that you don't have to dissolve the entire sample. You can really, with the laser, spot a specific part of the sample. So you can make the map of the contamination of the sample. That's, from my point of view, totally amazing. In this picture, for example, you can see the uranium contamination observed in some copper wires, and you see exactly where the contamination is located. Okay, you can have map assaying all the types of the materials. This is an example with the acrylic. Acrylic is quite hard to dissolve. Typically, you have to do dry ashing. In this case, with laser ablation, you can assay the sample in a relatively easy way, making the map or a certain matrix on the surface. And then you don't, not only you measure, you have the map of the contamination on the surface, you can also go deeper in the materials, disentangling the contamination that you have on surface from the contamination that you have on the bulk. That's extremely important if you want to assess independently the surface contamination, for example, from the radon plate out, from the contamination, intrinsic contamination of the bulk of the material. Okay, that's very good. That's very nice. Probably, it is certainly a fancy technique, but it's not the ultimate technique, because there is an important drawback that you don't know the mass of the ablated material. So you can ablate the material. So you have some material which can be it is evaporated and introduced in your spectrometer, but you don't know how much. So to quantify, you can let's say understand that you have a certain amount of contamination, but to quantify the actual contamination is very difficult. In principle, you should have samples with non-contamination, which are very hard to produce because you should have a sample for each material, because the amount of materials ablated depends on the laser, but depends on the samples, on the optical, mechanical, and its thermal properties. So since reference materials are not available in this technique, although good, although very nice, has to be used in it's something that can add information to something that you do with a standard ICP-MS. So those techniques are complementary. Figure of merit, there is no chemical preparation needed. It's not destructive technique, or nearly not destructive, because just you scratch a little bit the surface of the material. It is very fast, much faster even the ICP-MS. You get spatial information and low detection limits similar to ICP-MS. It has, let's say, some interference between atomic masses of the ions and the moleculars that you can eventually form in your system. That's the same as ICP-MS. And the main limitation is that you need a reference material, which sometimes can be available, but most of the time is not available. Now, since we have limited time, just a few words about the emission spectroscopy. Now, the basic concept, the take-home message.
Sorry, Roberto, just to give you a number. You have 2 minutes to 4:15, and afterwards, how much you need?
No, I think in 5 minutes I will be done.
Okay, fine.
I'll try to make it in 5 minutes. And
please go on.
So the idea is the following. Then we say that if we want to assay a material, we should, let's say, precisely define the process that we want to use in order to get the hint of this specific contamination. In case of the germanium is gamma emission. In case of the ICP-MS is basically we profit of the different mass between the sample that we have and the uranium and thorium, which are very high mass. They have a high mass. So another possible feature that we can exploit is the X-ray fluorescence. Basically, we stimulate the samples with an X-ray source, and then we detect the light emitter. So in this case, we have a spectroscopy detecting the light. These techniques is a fast technique. It allows a range of elements in a fast and stable way. It's typically, this is a machine that we have here, a CMAT in my lab. It's not, let's say, it's not very sensitive as the other one. It's typically used more for the elemental analysis or for the sample that can be assayed in ultra trace mode. Another hybrid technique is inductively coupled plasma with the atomic emission spectroscopy. It's kind of hybrid between the spectroscopy and the ICP-MS. We have a plasma, but then you measure the spectroscopy of the light emitted by the sample. These are examples of results. 2 minutes on the neutron activation analysis. This is becoming quite popular now. It allows the precise identification of the element at the level probably which is not cannot be achieved with other techniques. So its sensitivity is superior to germanium, can be superior to germanium and spectroscopy, mass spectroscopy. So this method is based on the conversion of a stable nuclei into radioactive nuclei by radiation with neutrons, and subsequent detection and identification of the radiation emitted by the activated nucleus. This is a sketch of the process. You have the neutrons, you activate the neutrons, for example, for neutron capture. Then after a certain time, this it can be the prompt emission of gammas with later with which you deoxidate the nucleus, and then the element decays through typically beta decay to another nuclei with the further emission of the radiation, which is typically called delayed gammas. So what you need is a strong source of neutrons and gamma detectors, and the detailed knowledge of neutrons capture reaction. The delayed neutron detection is typically the delay gammas neutron activation analysis is the most common for this method. We don't detect, unless specific case, the prompt gamma rays, but we just, after the radiation, take the sample to a low counting facility with germanium, and then we measure the gamma from the sample. Then from the lines that are emitted, we can precisely measure the contamination of the sample. Okay, we here a simple formula just to get the feeling. You measure the rate of emission of gammas, then knowing the effective cross-section and the integrated neutron flux, you can get an amount of contaminants in the original sample. Okay, the sensitivity strongly depends on the type of material, the neutron exposure time, and then the background that you have when you count the material. With this, in principle, you can measure both, either uranium, thorium, and potassium. Potassium, for example, is measured through neutron caption of potassium-41, which produce potassium-42, and then you can get the potassium-40 contamination from the natural abundance. Just few pictures of this technique. In principle, what you have obviously is a strong neutron source. This is now getting popular because of the availability of neutrons reactor with the high neutron flux. Okay, let's go directly to the figure of merit. We can get greater sensitivity than the direct gamma ray counting for very good to say potassium-40. Cons, we have a limitation because we have to prepare the sample. It cannot again measure the chain, and it's necessary to get irradiation standard. Okay, because you have to some sample that have to be irradiated in order to normalize your measurement in order to get quantitative results. Okay, there is just one method, but I simply skip this because maybe it's technical and we are over with time. I didn't have time really to go through the details about the radon, the lower decay chain. Okay, we say that we measure ICP-MS is the typical technique to measure the upper chain. The middle chain is typically can be measured with germanium from the gammas. For what do we do for the lower chain? There is little gammas that can be detected here. It's very hard to get a quantitative estimate of the lower chain contamination to verify or whether we have the equilibrium, or better to measure this part when the equilibrium is broken. The only technique I'm aware of, or at least the best technique I'm aware of, is the radiochemical separation on polonium. I won't go through the details of this technique. The only, let's say, message that I want to pass, the take-home message, is that radiochemistry now is so good that we can dissolve and then separate the single elements from the sample, getting rid of everything else and just keeping the polonium. Polonium is a good, it's a known alpha emitter. It has a very clear alpha emission lines. This can be measured just depositing the solution with the leftover of the dissolution on the source and then counting it with the alpha spectrometer. So PRONS is the only technique able to measure the lower change, but it requires some tedious sample preparation. I'm done. Basically, I think, sorry for being 5 minutes late. There is no basic conclusion that I want to stress. Before I thought to put a kind of summary of the sensitivity of the technique, but I think this is a bit sterile as a conclusion, because the take-home message is that there is no technique better than the others. Everything is complementary. The assay campaign of low background experiment is a very hard job, very hard task. You need a lot of experience, you need a lot of resources to do that. And even the sensitivity that you can get for a specific technique strongly depends on the source, on the sample that you want to assay. Okay, so that's all. So as conclusion, just I report what I said at the beginning of this lecture. Hopefully we have known a little bit more about natural radioactivity, equilibrium, cosmogenic, radon, importance of the material assay, and techniques used to infer the contamination of the detector materials.
Thanks a lot, Roberto. Very nice presentation, I have to say. And I think that our students could understand very well what is the background and how to measure. And both are very difficult to, maybe the measurement is even a very big challenge indeed for the experiments that, for the level of background that one wants to reach. Very nice lecture, really. Okay, are there some questions, or we want to ask questions in the discussion afterwards? If a short one, we can ask. We can try to effort that. If not, maybe everybody wants to have a coffee, and Roberto also. And then let's restart. Let's have our coffee break now, and we will restart at 4:45. See you later.
Thank you.
Bye.
Bye-bye.
And thanks again to our...
maybe not very...
Marco, we cannot listen to you. Okay.
Thanks a lot, Gabriella and Roberto in particular. Very enlightening discussion, very enlightening presentation.
Yeah, very clear.
Yes.
Not easy. This is a matter that very often it's so difficult to explain sometimes. So really, congratulations to Roberto. Okay. So now we go to our coffee break, and we will meet again for the exercise in 20 minutes from now about. Okay, see you.
Okay, thank you. Bye-bye.
Bye. Okay. Ready? Okay, so I guess we restart with the program, and it's a continuation today of the hands-on on statistics as started yesterday. So I see Pietro already there, and of course also Alessandro De Falco. Please go on. Pietro and Alessandro. Maybe Pietro is starting.
Okay, yeah. So
okay, please.
If Marco agrees, I think we can. So maybe we can start just asking some feedback from participants. So for you, for those that try to go on with the exercise, just to get a feeling where at which level you are, say, today, or if you encounter any problem. So maybe let's discuss the status, or if, for example, if you have any questions, so feel free to ask. If you wanna, I don't know, come back to some point that might not be clear, or you don't know, you don't understand how to proceed. I don't know. So just I think we can start with some feedback from you guys.
Yeah, indeed. I think just as a preliminary encouragement, I would like to encourage people to speak up. I mean, usually we think about this hands-on session with people around with their laptop, and me, Pietro, and others jumping here and there, being available, asking questions, and so on. So something very interactive. Of course, we are online, so it's not the same, but we need your help to get some feedback and help you in a better way. So I see there is already a raised hand. So Robert, please.
Yes, thanks a lot. So first of all, feedback. I really like the notebook. I think this really is really nice to get a feeling of how to do such an analysis. And I also really like that you give like this very basic notebook where one really needs to. I think one already needs to know some things, and then the ones with some hints and the solutions. So for me, this was really nice. I now did it until paragraph 3. And I do have one question concerning the test statistic, because maybe I did it wrong, but so the test statistic doesn't seem to be monotonous. And I was wondering if this is a problem or not, because so intuitively I would say this might be a problem.
Okay, in principle it should be monotonous. So what do you mean exactly? Maybe you can share your screen just to show us what you get.
Maybe maybe I just screwed up the something somewhere, but this is what I get for the so for the observed mu as so the test statistic is a function of the mu. Maybe also maybe others.
Okay, so mu obs is the maximum likelihood estimator.
Yes, exactly. Yes. So this is the mu. I just run through 0 to 20, put this in. The tested one is then fixed to the values that are provided in this data frame. And then I put this in, let's see, this test statistic function, which I define somewhere up here. Yeah. This is just so this is the best fit and the tested one. And I just plug this into the ratio, the likely ratio.
Okay. Yeah, so it looks okay. So I'm not used to look at this kind of dependencies of ops versus the statistic. Can you go back?
I mean, there's no I didn't see any issues afterwards when I was then also computing the p-values. Everything seemed to be working properly. I was just wondering why this is not 1/20th.
So so I don't know. I don't have an answer at the end. I think so. You can see that for maximum likelihood estimate or larger than your tested hypothesis, you get Q equal to 0, and that's fine.
Yes.
Then it's okay. Then it's bigger, and it's smaller. And it goes to 0.
Maybe if somebody else has this open, this notebook open, one could quickly check if I just made a mistake somewhere or if this is really correct. But I think so. The reason why I thought this might be an issue is if I would do if I would test the performance, or let's say if I run through this distribution and I observe, or I expect 15 or let's say 13 events, and my best fit is 0, then I would get a higher p-value than if I would get 3.
Yeah, exactly. So I think there should be some pathology, because I also would expect that a statistic will higher values when you go to smaller fitted signals. So I think this this could be due to the minimization. Maybe that's the first thing that comes to my mind, because it can happen when you have very small signals in your data. So one issue that can arise is that you can end up with so negative values in the likelihood function itself. So because I guess you define the logarithm of the likelihood function, and it can happen that you get so maybe if you go to your definition of the likelihood function.
That's not very nice. Well, yes, the test one. You in likelihood function, the test statistic, right? Yes. So.
Yeah. So, for example, so this is the last term is called logarithm term, and I think that sometimes it can happen that the argument of the logarithm can be negative, in particular for small signals, because for when you have small signals, you so in principle you can also have negative value for MUSI, and so I'm thinking if this can affect.
No, but this is not. So music in this case is fixed, right? So let me see. Maybe I like. I'm still not entirely sure if I can screw up something on the way, because it's not the best. But
so you also get.
I mean, in principle, this is just take. So the mu's are fixed and defined above, right? Now the
yes, those ones that you are testing.
That this likelihood depends on this data set.
Yes.
Wait. Okay. No, I think. All right. I think. Let's see. I think. Okay, this data set is the data set that you provided with the best fit of 2.7,
Okay.
And if I think this is also the value that we see here, right? The maximum.
Yeah.
Let me very quickly think.
So one thing that one can do is like, adding a control on that arguments of logarithm parts of the likelihood function to check if you get negative values there, because so I'm not entirely sure about what happened, but I think so I don't know what I think it happens that if you compute the likelihood function and there is a negative argument for a likelihood, so I think Python should get you not a number. But then I'm not sure how this is handled by the minimizer. And maybe this can screw up.
Drops out in the sun.
Yeah,
probably.
So that the argument is the logarithm can be
already more in the sun. Yes, yeah, this might be.
So one thing that I would do is checking if you, for example, during the minimization you get negative values there, and for example, if that happens, you can try to to discard those cases and see if this behavior of the statistic is still there, or it becomes monotonic as you expect. So you can discard, for example, just by assigning a huge value to the likelihood, so that, for example, for the minimizer, this would be considered as a basically bad point.
Mm-hmm.
This is one test.
Right. Yeah.
But this is actually a nice point. So this would deserve some investigation.
Yes. Okay. All right. Now
okay. Let's try to see if we can help Robert maybe offline in a while, and hear if there are any other general questions. And thanks for your feedback, of course.
Yes, I have a question, if I can. I'm Claudia De Dominicis.
Yeah.
Okay, so in the last part of the exercise, so when we compute the exclusion limit, we are doing this only for a single toy experiment. So we are doing, we simulate only one simulation of an experiment, so without a signal, right? And then we compute the maximum likelihood estimator, and then through this we compute the Q for each assumption on mu. And so my question is, here we are only simulating a sample for the concerning the data without a signal, but so this is how we behave if we are taking data in real life, so a real experiment. But if we don't have if we want to compute the expected exclusion limit, we should do more toy Monte Carlo simulations, right?
Yeah, so,
okay.
So let me say, just first of all, so now if you use the dataset I provided you, so in principle, you don't know if there is signal or not. Okay, you just have a given number of events distributed in your analysis space. So
okay.
I produced just as one point of the exercise was requesting, like just writing a routine to generate a dataset.
And you assume zero.
I won't tell you if I injected signal there or not.
Okay.
But
okay.
You don't know in principle, and that's basically, yeah, the real situation. So you take data with your experiment, you get some data, you don't know where they come from. So you have no idea on an event by event basis what is what. So you just have a data set, and you perform the analysis that you did. Then coming to your question, so yes, that's a good question, and that's actually the last part of this exercise. So this is all about performing a statistical inference on a given data set. So in general, on an observed data set. So here you have just a fake simulated data set. In reality, you will have a real, so the real data acquired by the experiment. And then if you want to, if you want to understand what's the exclusion limit that you can get by an experiment before building the experiment, that's what is called sensitivity of an experiment. And that's that's in the final part of the exercise, but that's exactly about what you were thinking about. So it's simulating all the possible, so these many possible outcomes of your experiment under the background only hypothesis. So assuming that there is no signal, you can simulate many toy Monte Carlos. Then you study all the possible exclusion limits that you can get. And so you get some distributions, and you can basically evaluate the distribution of exclusion limits that you get with your experiment under the null hypothesis or under the background null hypothesis. And based on that, you can basically derive the expected sensitivity of the experiment. That means you basically compute the expected distribution of exclusion limits that you can get by your experiment. One usually, for example, refers to the sensitivity as the median of the distribution of the expected exclusion limits. But I think we will come to this later today. I will explain in detail. So that's part of the exercise, actually, how to make this further step and how to study the sensitivity.
So basically, you are saying that you simulate the distribution of Q mu for the background only hypothesis, and then you have the distribution for the signal hypothesis, and then you take the median of the background distribution of Q mu, and you integrate from this to calculate the p-value.
Exactly.
Okay. Exactly. And another very quick question: when you I forgot where this point. Okay, when you minimize the likelihood, maybe this is due to the fact that I don't know Python, but when you calculate you minimize the log likelihood, so you, for example, in the last part of the exercise, you do fit res equal to minimize log likelihood. And then the second argument that of the function minimize is the mu signal, but this is only a starting point to give to the function to minimize, right? You're not. It's
yes, exactly. So okay. You basically need to you can give two arguments. So the first one is the initial guess of the parameters values.
Sorry, can you share the screen while you discuss this, such that you point directly to the likelihood and the various parameters? I think it can be more clear also for the others.
Yes.
Thanks.
Okay, so here, this is the last step of the exercise of yesterday, so the first part of the exercise. And where is it? Somewhere. Okay, here we have to calculate to minimize the log likelihood. And so we give this input here. That is, and this is only to give a hint to the minimizer function. I mean, this is the starting point to minimize. Is not. We are not telling him that the mu sig is some certain value.
Yeah, exactly. So also a suggestion for those that are not really experts with Jupyter notebooks, if you are inside a function with your cursor, you can hit Shift Tab, and this will give you some information about the function itself. Like you can try like.
Okay. Okay. And so because at the beginning we simulated the sample with a certain music, but then in this last part we are not using signal in some way because we are running over different.
Exactly.
choices.
So that's
Okay.
so if you, for example, if you look at the documentation of this minimize method, you will find a list of the arguments. But so I can tell you that the first argument is the function to minimize. The second one is the initial guess for the parameters. So this is okay. You have there just music, but you can put even 1 or 10 or. This is important just to help the minimizer to find a way to minimize the function in a reasonable number of tries, basically, because in principle the initial parameter value can span in the an infinite range. So and what the minimizer does is just find it does several tries, changing the value of the parameters, compute the likelihood, in this case the log functions, and see if there is a trend that minimizes the function. So and of course, in your case, if you have music like I don't know equal to 20 or equal to 10, and your data fits 10 events, so the minimizer will understand that going lower from 20 to 10, the function minimized. But if the initial parameter value is like 10 to the 50, then it tries 10 to the 49, or it tries 10 to the 51 and goes around there, but starting very far away from the best fit value. Basically, the minimizer will never find a gradient for the function minimization, and so it will just stop after some tries. That depends on the algorithm that's used. So this is just useful to give some initial value that it's not super far away from what you expect to be the best fit value. So it can be music in this case. You can try even with 150 maybe. But if you
okay, yeah, sorry. No, I was wondering how can you choose music, because as you said before, I don't know how you simulated the I mean, I don't know so you use the initial estimation that we did, so like 5 events and so on for a dark matter particle of I don't remember 50.
So there you can basically put whatever you want.
Okay.
So just to get a feeling, so you already know by the statistic distributions that are available that they span signal hypotheses between 0.1 and 20. So you already can understand from there that that's the range of sensible signal strengths in your case. So you might expect that your signal strength is within this range. So whatever value in that order of magnitude should be fine for the minimizer to converge. And if you, for example, if you don't give this initial parameter value, probably the algorithm of the minimizer would start really like from 10 to the 40 or something like that. No. So it's just useful to help the minimizer to converge.
Okay. Thank you. Sorry for this long.
This is a typical trick for the minimization in real life. Also the boundaries, so you can set also, you can see that from the code you found that there was a boundary also set for the parameters. So the second argument, it was bound, and that also helps. So you don't want to make a constraint fit. So you want to you don't want to constrain your move parameter to some values, some range. But it's useful to provide some range, even a large one, but provide some range to help the minimizer again to stay in a confined region of the parameter space. The principle can be infinite. So this is just technically a trick that in almost every case is needed for a minimization algorithm to converge.
Yeah, and definitely the minimization is one of the trickiest part of the real exercise. So is there any other general question on the topics of yesterday? And by the way, thanks for both your points, which allowed to come back to yesterday and start again. So if not, maybe Pietro can quickly recap at least the last part of yesterday. So what has been discussed now, how you get the upper limit from one single outcome of your experiment, and then its extension to the profile likelihood and the sensitivity. And so we go to the second part of the exercise.
Okay.
Pietro, if you can, please speak up a little bit.
Yep. Okay. Can you hear me well?
Yes.
Okay. So maybe just before starting again, just a technical announcement. I don't know if so there some people encounter some technical issue reading pandas data frames from the pickle files that had the example data set and the statistic distributions. So just to say to everybody that, so there was a discussion on the Slack channel, but just to make everybody is aware, in case you had problems in reading those data frames from the pickle files, I also produced CSV version of those data. So instead of a pickle file, it's a CSV. And you can find in the Slack channel some basic instructions. So you can basically read with pandas the CSV files instead of the pickle files, and basically read data in this format to fill a data frame. So it's just a workaround to in case you had this kind of technical problem. If you have in general any problem, okay, feel free to ask in the Slack channel at any time or here, of course. Okay, so that's said. Okay, we can come back. So as Marco said, quickly to the second part of the exercise. So the first part was all about building your physical model, and then once you have that, you had to define so the likelihood function, the likelihood ratio of the statistic, but the Q mu, and then to make statistical inference on a given data set, what you need is the statistic distribution under the signal hypothesis, because you want to study what's the significance of the rejection of the signal hypothesis. So what you do is so taking so studying some signal hypothesis, each of them will have the statistic distribution. So, and on your data set, you evaluate the test statistic value under each hypothesis, and you compute the p-value so of that basically gives the significance of the rejection of a given signal hypothesis based on the observation, on the observed data that's given by the test statistic value on the observed data set. So for each hypothesis, you can compute this p-value, and then your exclusion limit at a given confidence level, it will be just the signal strength corresponding to a p-value that you're looking for, in this case, for a 90% confidence level, exclusion limit, the value is 0.1. So you can look at the p-value for each signal hypothesis, and then you get a curve like this. You can find this way your exclusion limit. So I don't know. Hope it's quite clear for everybody. But if there is any doubt, please ask now. Okay, so if not, I think now we can move on in the from the simple likelihood ratio to the profile likelihood ratio, and this is like a more general treatment of your statistical inference in general, because the profile likelihood allows you to introduce systematic uncertainties, and of course, again, what you have in this exercise is not the most general case, so I just chose some a simple case just for you to have to try out and play with something feasible in a reasonable time, let's say. So what you can do now is just introducing systematic uncertainties on the background rates. So in general, you can have systematic uncertainties not only on the rate of background, but also on the shapes, for example. In this case, this is the most simple case. The uncertainty is only on the rate. So for example, here I just put some more or less random uncertainties, so like 40% on the ER background rate and 50% on the nuclear recall rate, on the nuclear recall background rate. And so this means that you can now introduce nuisance parameters. We call here T for both background types. Basically, you can parameterize this the dependency of the expectation value of your model component from the uncertainty, the systematic uncertainty you have, through the nuisance parameter with this expression. So, so before this, you just had an expectation value that was depending, of course, on the rate. So you expected a given number of electronic recoil background and nuclear recoil background. Now, since you have this uncertainty on the rate with this expression, you basically allow the expectation value of your backgrounds to change, and this value can change according to the size of the extent of the systematic uncertainty this way. So basically, you are assuming here, and that's a usual, very common assumption, basically that your uncertainty represents so can be thought as a Gaussian distribution of the nuisance parameter, where, for example, in this case, you can think that the nuisance parameters are Gaussian distributed, and when the nuisance parameter value is 1, this would correspond to a 1 sigma deviation with respect to the nominal value of your expectation value, where sigma, of course, again is different for depending on the systematic uncertainty you have. Okay, so this is how your expectation value changes as a function of the nuisance parameters. And then what changes is that now when you perform your likelihood fits, you basically have two different kinds of fit that you can do. So before, you were just saying, okay, I fix the signal hypothesis, so I compute the likelihood ratio, where the first likelihood was just a function of the fixed signal hypothesis, and the second term was the unconstrained fit of your parameter of interest. Now, your likelihood function in general will depend not only on the parameter of interest mu, but also on the nuisance parameters by this dependency, basically. So what you do now when for define the profile likelihood statistic is again a likelihood ratio, but now you have the unconstrained or unconditional maximum likelihood, is this one, where you basically fit your data with no constraints on any parameter. So you fit simultaneously all these three parameters, so the parameter of interest and the nuisance parameters. And so you usually see the maximum likelihood estimator and conditional maximum likelihood estimator are usually indicated by hat. So you basically have likelihood as a function of mu hat and t hat, and the first term of the likelihood ratio will be now a conditional fit. So what you do is to profile out the nuisance parameter. So you fix your signal hypothesis mu, but you fit this time your data by looking at the maximum likelihood as a function of the nuisance parameters. So you call the maximum likelihood estimators of nuisance parameters in this case are called as double hat typically. Okay, and then so besides that, the definition of the statistic is basically the same, but now you have like more degrees of freedom related to the nuisance parameters that comes into the game. So and then that's basically it. So this next part of the exercise, in this next part of the exercise, you just need to basically introduce this nuisance parameter. So write a new likelihood function or extend the definition that you had before, just to allow for the dependency on the nuisance parameters. Again, define a new statistic, in this case, the profile likelihood ratio, and after that, basically the procedure for the statistical inference is basically what you already did before. So here just some additional information about the nuisance parameter. So yeah, that's what I said before. One tip can be that you might want to fix a lower bound to the nuisance parameter value, because as we said, they are Gaussian distributed. So of course they can take any value larger or smaller than 0. But of course, if you get negative value for the statistic, you might end up to a negative value of to a negative expectation value of your background in this case, depending on the systematic uncertainties. If you consider, for example, the uncertainty on the nuclear recoil background. So if you for a nuisance parameter value of -2, basically you have an expectation value for the nuclear recoil background of 0, and if the test statistic is smaller than -2, you would have negative values which are unfeasible, and this comes into play when you generate a toy data set now, because the generation is again basically the same, but there is a small complication, because now you want to so not only randomly generate the number of signal and backgrounds, but now before doing that for the backgrounds in this case, since you have the nuisance parameters that affect the expectation value, you should first sample or generate a random value for the nuisance parameters. So you do now a Gaussian sampling of the nuisance parameter value. So previously, for the simple case, you just basically, you can imagine this is exactly the same case where you have nuisance parameters always equal to 0. But now you can just sample from a Gaussian, so you can get values different from 0. This will change your expectation value accordingly, and then you can sample from a Poissonian distribution, the number of background events. And this will change for any random generation of your data set. So that's where it comes into play, this boundary on the nuisance parameter value. So you can set this boundary to avoid a negative expectation value when you generate random data. Okay. So in this case, you can just practically, for the exercise, you can write a new routine to generate the data set, or again extend the previous one that you wrote. So coming to the likelihood function, so as we said, now it's a little bit more complicated. It depends on these three parameters. So where the dependency on the nuisance parameters, so is first of all on the expectation values that comes into play in the likelihood definition. So of course, this mu background depends on T, but then also you have now to add basically a term that is related to the probability for a given nuisance parameter value, because your probability is basically maximum for the nominal nuisance parameter value, so the central one, so 0. But of course, if you consider deviation of this value, you basically need to consider that, so to consider that value is less likely, or is, let's say, less expected than the nominal one. So basically add a Gaussian term, Gaussian probability term to the likelihood, and if you consider the minus 2 logarithm of the likelihood, basically this transforms into this simple term. So basically the difference of the nuisance parameter value with respect to the nominal one squared. You can just very simply get this by the logarithm of a Gaussian distribution. So you will have these two additional Gaussian penalty terms for the nuisance parameter in your likelihood. Okay, so this is basically the main difference with respect to the previous case, and then you're basically done. So you will define the test statistic basically according to this expression. Now you can try out yourself to perform now the two types of fits of maximum likelihood estimations. You can compare with the previous, so on the same data set, you can now compare what you get from the minimization of the simple likelihood, so without nuisance parameters. You can see what you get now with an unconditional fit. You can see what you get with a conditional fit, and you can check what comes out. Then you're basically done. So again, then when you have the test statistic definition set, you basically can do the same statistical inference by exactly how you did before. So what you need is again the test statistic distribution under the signal hypothesis. Of course, in general, this is different from the test statistic distribution. This can be different from the statistic distribution of the likelihood ratio. So what one does is just estimating this distribution by Toy Monte Carlos in this case. But again, you will have already the test statistic distributions here in the same file that you already used. So you will see here there are just the same distribution here with just this PLR, so profile likelihood ratio. I think we will have with a little bit less points. So if you wanna do something more precise or more interesting, you can, as I suggested, also to try to estimate this distribution by yourself. So writing out. So this will take time. As I said already, it's a very computationally expensive calculation. It was already like this for the likelihood ratio. In this case, for the profile likelihood ratio, it will be even more expensive because now you have minimization, a more complicated minimization. So it will take more time. So just here I have a printout, just a single example. So you see the simple likelihood fit. In that case, it took 1.8 seconds, and the unconstrained profile likelihood fit took 2.5. Actually, the difference of experience in this for this specific statistical model can take up to 2 or 3 times more for a profile likelihood fit than for a simple likelihood fit. So this is a computational expensive step, but you can try to do it, and then you can make your program. So there's no book running over the night. You can check something, some additional distribution for additional signal hypothesis that what you find in the file, right? And then that's it. So you can compute again the exclusion limit on a given data set. The procedure is exactly the same. So for each signal hypothesis, you have the statistic distribution. You look for the statistic observed value on the data set, and you will obtain the exclusion limit at 90% confidence level as before. So maybe an additional information is that so in general, of course, you expect that when you take into account systematic uncertainties, this will make your limit weaker than with respect to the simple case where you had no systematic uncertainties on the background. So this is in general true. Of course, to which extent depends a lot on the model itself and on the extent of the systematics. In this case, for this specific case, the systematics are not, so the impact, you shouldn't expect a huge impact. So, because, okay, the systematic of 40, 50% on the rate of the background is not super small, but it's not even super big. And so you can expect probably just a few percent of worsening of the limit with the profile likelihood ratio method with respect to the algorithm. But I think the point of this is mostly to see how you in practice can deal with systematic uncertainties and how you can deal with a profile likelihood ratio in general, where there are nuisance parameters in the game. So that's it for this section. I don't know if there are questions or doubts or something not clear.
Probably it's just time to put really the hands on the exercise. So if you want to explain quickly how to deal with the general sensitivity that was mentioned before, and then we can have the student go on with their own exercise, and we stay available online.
Okay, so so as we just said before with Claudia, so up to this point, you see what you need to compute on the exclusion limit on a single data set. Then when it comes to study the sensitivity, it's what we said before. So you want to know what's the expected exclusion limit from your experiment based on your physical model, so based on your signal expectation, on your background expectation. What would be the expected exclusion limit under the null hypothesis? So if you assume that there is no signal, in general, you can have, as you see from the random generation, you can expect the outcome of an experiment, so the data that you find can fluctuate and different. So, and the limit will be always different for different data sets. But and then this will give you a distribution of the expected exclusion limits. So what you do to study the sensitivity is basically, instead of dealing with one data set, is simulating many data sets under the null hypothesis, so on H0 hypothesis, where basically you simulate data sets with zero signal expectation value, and you see what's the exclusion limits that you get. So you simulate this many times, and basically what you can estimate this way is the distribution of the test statistic QMU for all the various signal hypotheses under the null hypothesis. Okay, so what you get is something like this. So in blue is what you already know. Now is the test statistic distribution under the signal hypothesis. But then if you study this by generating data sets with no signal injected, you can study the distribution under the null hypothesis. And this distribution will be, of course, in principle different. And for increasing signal hypothesis, this will be more and more different with respect to the half chi-square or less distribution. So if you do this, you basically are all set now, because you have a distribution of the statistic outcomes under the background only hypothesis. So, and this, as you saw now, this will correspond to a distribution of exclusion limits. Okay, and you can study this by looking at some percentiles of these distributions. So you can say, you can look at the median the statistic value of the distribution of the statistic under the null hypothesis. You can say basically, on average, I expect that that my test statistic value is like this under the various hypotheses, under the various tested signals. And so when you come to the sensitivity, you can basically repeat what you did before, just by fixing a percentile of the statistic distribution under the null hypothesis, and again doing what you did before. So looking for the signal hypothesis for which you get a p-value of 0.1, and then in this way you basically can do this. So one usually does this for the median value of the distribution. That's what is referred to as sensitivity of an experiment. But if you look at the tails of the statistic distribution, so for example, 1 sigma, minus 1 sigma, plus 2 sigma, minus 2 sigma, you basically find what's the exclusion limit corresponding to, when you go to the tail of your expected distribution of the outcomes under the null hypothesis. And basically you can estimate not only the median value, so not only the median sensitivity, but also the 1 and 2 sigma bands. So what you usually have here, so the usual Brazilian flag bands. So this one. So in this case, for example, this central line is the median sensitivity, and then the green band is the 1 sigma band, and the yellow one is the 2 sigma band.
Okay, I would suggest. I think there is enough meat for today, and of course there are other relevant points that can be considered as an extension. And as said, we will not disappear after the school, but in case we are available for questions or to help you going on with the full exercise. Probably
yes,
for today.
Just let me say that if you are interested in your time, if you are willing to, already in the notebook you find some additional steps with some additional information, so you can go there by yourself, as Marco said, to work on that, and feel free to spend any time.
Okay, so it's 20 to 6. I think you can put your hands on. Really, we are here in the Zoom room. We are available on Slack, and we can reconvene at maybe 6:20 to see if there are any questions, and then we have the final discussion session of today. Okay. And of course, if there are questions, or if already you have questions, please speak up.
I would have a technical question about the likelihood itself. If that's okay. Can you hear me?
Yes.
Okay, sorry. So, right, the likelihood, you have this normal, like, extended unbound likelihood, and it's a two-dimensional, right, over S1 and Y. Alternatively, would it be equivalent to just cut on the Y value? So, right, you can keep 50% of the signal and reject like 95% of the background, I think, and then do the same in one dimensions, but with much less events, or do you like lose information?
So you mean basically doing an
So then
arcade?
then your toy data set is just like five events or something.
Yes.
Or 6.
So you are saying like that, for example, you cut here.
Yeah.
Yeah. So no, this will not be the same. Of course, in principle, all the events that are very far away from signal expected distribution does not play a significant role. So, for example, if you cut only very far away events, you don't lose much information. But in general, if you apply an hard cut, you lose a little bit of information in general because you don't account to what happens close to still your signal region.
Yeah.
Okay, so because you expect, of course, the signal to be distributed around this mean value here. So that's what was done earlier on, but it was like that's a way to simplify your life. So yes, you work in this case in a one-dimensional space instead of a two-dimensional space. But basically, you don't fully exploit the power of likelihood analysis, because likelihood analysis is most powerful when you, in the case you can model your signal and your background, and basically in that case you're exploiting the most of the information as you can.
Okay. Yeah.
Because you basically have the distributions of any component in the full analysis space, and so you can assign a probability for each event wherever in that space. So the probability can be very small but still non-zero, and for many events, like for this case of electronic recoil backgrounds, they can still add information even if they are not on the holy side, or let's say below the nuclear recoil median here. So one can do this. So that's what was done before. That was simplified analysis, a little bit less powerful, let's say. In general, if you're not able, or if you're not super sure of your background model, because all of this relies on your background model, right? So,
yeah.
And you need a robust model. You have to trust your model, and because you basically all the statistical inference relies on the background PDFs. In the case you don't trust very much, or you are not able, or you have some difficulties in modeling your backgrounds because you have peculiar sources or something that, again, that's difficult to model, you might go into that direction also for that, because you wouldn't trust a full profile likelihood analysis because you're not sure about your model. Then you would prefer to make an upcut and just remove all what you can, even if you sacrifice signal acceptance, and you restrict as much as possible your analysis to a portion where you really expect the smallest number of events, basically, with good signal acceptance. And you can even do, instead of a 1D analysis in S1, you can even do just a box counting, right? So you can select this region here and just count how many events you see, with no information about the PDF in S1. So this the various steps you can do. So step 0, let's say, is just a box counting, where you just count how many events you have in a given box, given region of your analysis space, regardless the shape of signal and background. Or if you're able to model in as many as you can parameters, your model, you can have a more powerful analysis if you exploit the whole information from the models in all the parameters that you're able to model.
Okay, yeah, now I understand. Thanks. That's,
So it's 20 minutes past 6. We can reconvene to see if you have any questions or comments after playing with the exercise. Is someone willing to show us his notebook, even if it's not complete? We had some interactions on Slack. Okay, Robert probably solved this issue with the distribution of the test statistics. And also then Maxime asked about the procedure to derive the limit for the various WIMP masses. So let's see, did somebody manage to complete the implementation of the profile likelihood? You can also tell us if you had problems and where your problems are. You can give it a try.
Probably I don't know. I can say just a few words. So of course, this is pretty big exercise. So there's a lot of things that you can do. So I hope this is just that a matter of time to implement stuff and try out. But I just can add that this exercise is for sure kind of oversized for the needs of 2 days of this school, but you can take this as a reference also for if you want to expand your interest in this side, if you want to do further studies, you can have this as like a basic reference for all the like fundamental ingredients of statistical inference with profile likelihood ratios, basically. Then you can expand as you want. It's very like if you go fully through this notebook, it's almost a master thesis job. So don't be scared if you're not at the conclusion, of course.
Indeed, when we prepared the structure of the exercise, we thought that it was probably more relevant to put all the ingredients inside, even if they could not be covered inside the 2 slots that we had yesterday and today. But in this way, you can have it there and you can play with it. Indeed, in any of your experiments, you will end up with getting out the results, and this is the basic skeleton of what you need. You can simply modify the physics model that Pietro explained, that is taken from our Xenon 1-ton. You can put your 1-dimensional, 2-dimensional model and get your result. The other secondary but not less relevant goal was to introduce some basics of this Python and notebook Jupyter approach that is quite easy and quite common so far. And this is another take-home message that one can put in his pocket at the end of the school. Of course, this is just a starting point, and then you can expand by your own.
Just out of curiosity, is there anybody that tried to write his code in a different environment, or a different language or tool?
So I don't know if this counts, but because I'm very unfamiliar with pandas, I basically converted everything to NumPy and then continued from there.
Okay. Yeah,
but I think it's probably a better solution to learn how pandas work. So just, I think in the few hours.
Yeah, I mean, for this specific,
but it seems really cool. I mean, I hadn't seen the data frames with the labels inside of the arrays, basically.
Yeah, I mean, for this specific application, actually, probably pandas is an overkill because it's not really needed. You have just few arrays. So even with NumPy, you can, maybe it's even simpler. But in general, pandas is a very powerful, gives you a very powerful structure. So data frames, in particular, when you have big data sets, it's really useful. So yeah, that's something that that's pretty powerful and that's extensively used in general to deal with data, especially when you, for example, so now we are dealing with also with small data sets, but for example, in your experiment, when you start analyzing data and you have like billions or millions or a lot of events to analyze, and then you want to apply some cuts and study populations, then dealing with pandas data frames can help a lot. And maybe as a general disclaimer, I can add one thing. So what you see in this notebook, so as we said, is a general and basic recipe to perform a statistical inference in the frequentist approach. And what you see here is also that when you study the sensitivity, or if you really go to the bottom of the exercise and you get to the discovery potential, which is the counterpart. So for the sensitivity, you deal with exclusion limits, where you want to reject the signal hypothesis, but you have exactly the counterpart, where you want to test your data or see what's the potential of your experiments in terms of discovery, so in terms of rejection of the background only hypothesis. So you can do what you see here in this example is that you can do both statistical inferences in a separate way, but here you make a choice a priori. So if you want to go for exclusion or for discovery, then this has some problems. So probably a more robust way is then going for the Feldman-Casing constructions of intervals, where you avoid this kind of a little bit problematic thing to choose a priori if you want to test for exclusion or for discovery. For Feldman-Casing construction gives you a way to unify the two things, so to avoid the so-called flip-flop problem. Okay, I don't want to go into detail, but just to let you know a little bit of the background. this topic.
Yeah.
Of course, if you want to learn more, there's more to learn besides this notebook. But this is like the starting point.
It was mentioned indeed in Oliviero's lectures about this flip-flop, and the Feldman-Clausen was one of the preferred way to overcome it. As he said, so he showed the simplified version with just one parameter. Of course, when you increase the complication in the model as the simple one that we presented in the exercise, then also the Feldman-Clausen construction become more complex, but it is doable. This is what we do in Xenon. And it was also a sort of overall receipt agreed with the other players in the, at least in the direct dark matter search community with LZ, DarkSide, and so on. So it's 6:30. So I think we can give back the stick to the chair, to Gabriella, for the discussion session.
Here I am, indeed. Okay, so this afternoon, maybe people already, this afternoon we have we have Roberto. So we ask him to be, is there? Roberto is there? Let me see.
I don't see him.
Roberto is not there at the moment. We can try to find him. You can contact him, Marco.
I'll try. Anyway, usually we try to have the discussion session even if the lecturers were not
fine. Okay.
present. Maybe
Absolutely. Okay, fine. Well, let's ask. So we had this very nice, really have to say, very nice presentation on the.
Sorry, Gabriella, I made a mistake. We usually have the discussion session in a different room, and so no, my bad. I will link the proper Zoom here in the chat, and then we move to the other one.
Okay, fine.
Francesca, if you have it.
Okay, link to.
Yes, great. Okay, so we move to the other room.
Okay, the one that Francesca sent.
Yes, exactly.
Okay, maybe we